This is part 1 of Advanced Functions Complete Exam Review. So this is what I'm going to be going over in this video. I'll have a time stamped there that you can see, so you can skip ahead if you want to just point out certain things. This is like the first unit right here. It's just kind of like a review of functions, and then after that it goes into part 1 of polynomial functions. So first half is just describing what a function is and all the basic information, and then part 2 will be more about polynomial functions. Okay, so to start, what is a function? The way I would describe a function is that for any input value for x, there is only one output value for y. So that may sound a little bit confusing, but here I'll give an example. So let's say f of x equals some number, right? Equals whatever it is. If you set x equal to, let's say 2 for example, so if x equals 2, there can only be one output value possible. Okay, so let's say that equals 4. Every time you put in 2 into this value here, it'll always equal 4, no matter what it is. And let's say you put in, say, like 3 into that value, so 3 into this x value here. No matter how many times you put in 3, you'll always get the same answer. Let's say it's like 5 for example. So just to do a visualizer there, so if I have a graph right here, and then I draw a function, let's just say a straight line across like this. So if I set an x value in here, let's say this one right here, so x equals 1, there's no other x equals 1 in the entire graph, right? So along this entire line here where x equals 1, there's no other values. So every time x equals 1, you always get this number right there, no other numbers. That being said, if let's say you had a graph or a function, well, it wouldn't actually be a function. Let's say you had something that looked like this, and you say, well, x equals 1 right here. There's also another point right there where x equals 1. So you would have two values for the same x value, right? So that brings you to the vertical line test, which basically just means that if you have a equation like this, you can just put a line across, and then if there's 2 points on the graph that hit that vertical line, it's not a function. So let's say you had a circle, for example. You put a line across, you can see there's 2 points, so a circle is not a function. But if you had like a parabola, for example, then you can just put a line across, and you can see there's only 1 point. Anyways, I'm going to skip ahead to the next point, which is finding values of a function at any x value. Alright, so I have the second part written in here. So there's two functions here, so f of x, which is this one right there, and then g of x. So the first question here is asking to find f of 3. So when x equals 3, what would the value of this function be? So whatever number is inside the brackets here is the number you're going to replace with x. So we can see the original one was f of x, right? So x can equal any number. So you're going to replace all the points where x is, so for example right there and right there, with number 3. So here I'll skip ahead to show what that looks like. Okay, so we can see that every point that had x in it, I just replaced with 3. So see, I replaced x there with 3. And now it's very simple after this. You're just going to basically just simple math to solve this. So this, for example, 3 times 3, or 3 squared is 9, times 3 is 27. This one, 2 times 3 is 6. And then minus 1. So then you just add them all together and subtract 1. So this would be 32, I believe. Yeah, 32. And then, so this next one here, so it's asking when is, for g of x, if you replace x with a negative 2. So again, This one's a little bit simpler. You're just going to replace x here with -2. So I'll skip ahead and do that. Okay, so this one a little bit more straightforward. This obviously equals -6, and then you just add 2, and you will get -4. So that part is pretty straightforward. Should all make sense. So you just replace x with whatever value is in here or in there. This one's a little bit harder. So first off, we're saying f of g of x. So this is it might be a little bit confusing, but basically what this is saying is that every time x appears, so back up here, every time x appears in that equation, you're going to replace it with the equation of g of x. So you're going to replace every x, here I'll draw this in a different color. So every x right here is going to be replaced with this entire thing. So 3x plus 2. So I'm going to skip ahead to kind of show what that looks like. There we go. So every time x appeared here, I just replaced it with 3x plus 2. So this is going to be a little bit annoying to kind of expand. So I'll do that now. So this will be 3. And then if you remember how to expand this, so this squared basically just means that it's 3x plus 2. And then it is also being multiplied by 3x plus 2. So all that will equal, so you're going to multiply this in first, so that's 9x squared. And then 3x times 2x, you get plus 6x. And then 2 multiplied by 3x, so same thing again, plus 6x. And then 2 squared, so you get plus 4. That's all that is being multiplied by 3, so don't forget those brackets. And then I'm just going to expand in the 2 here. This is going to become 6x plus 4. Okay. So what you're going to do now, you're going to multiply the 3 in here. So I'm going to skip ahead and do that. So just an FYI, so 6x plus 6x is obviously 12x. Alright, now you're just going to collect like terms. There we go. And now let's do the next part here. Yeah, and you're just going to leave it at that, so with the x's and all. The next part here is f of g of 2, which is a little bit more difficult because now we're not just setting x to anything, right? X actually has a value. So where we're at right now, it'd be very easy to just replace all these x values with 2 and then figure out what that equals, right? But on the exam, you probably wouldn't have done this first step right before. There probably wouldn't be a question asking to do this right before. So we're going to instead start from scratch. So f of g of 2 is basically saying whatever value of g of 2 here, replace all the x values in f of x with that value of g of 2. So what I would say you should do first is first find out what g of 2 equals. So we're going to replace x here with 2. So let's do that first. So g of 2 equals 3 times 2 plus 2, which just obviously equals 8. So now that we know what g of 2 equals, we can erase this kind of, so it's not g of 2 anymore. We're just going to replace it with 8. So now it's f of 8. Okay? That's not really what the question's asking, but they're identical. G of 2 equals 8. So we can replace f here, or f of g of 2 to just f of 8. So if we go up back here, we're just going to replace all the x values here with 8 now. So 3, sorry, f of 8 equals 3, 8 squared plus 2, 8 minus 1. Now if you put this number into your calculator, I believe you should get 27. Yeah, or 207, I mean, sorry. You should get 207. And now just to check our answer, let's go back to here and let's fill in all these x values here with 2. Okay, we're not going to do 8. You might think, well, we replace them with 8 here, so we have to replace them there with 8. But you have to remember, all the x's in this equation belong to g of x, okay, which is kind of a weird way of saying it, but all the x's there belong to g of x, which means, remember this x value right here, in the original question, it was f of g of 2, right? So this x value should actually equal 2, not 8. So all these numbers here are going to be replaced with, or all these x's here are going to be replaced with 2. So f of g of 2 is going to equal 27, and then 2 squared plus 42 times 2 plus 15, which I already checked, it also equals 207. Alright, let's do some transformations. So I have this function here with all these unknown variables. There's a whole bunch of them here. And let's just break down what all these variables will mean. And then you can also have like a squared up here or a cubed. Doesn't matter. So it doesn't matter what the power of this function is. It's just, this is what all the variables mean. So k in front here, that is going to be the vertical stretch or compression. So if k is a decimal number, so if it's like 0.5 or 1 over 2, then it's going to be a compression, okay, not a stretch. But if the number is, let's say like 2 or 3 or 2 over 3, so basically any number above 1 or less than -1, then it will be a stretch. But if it's under 1, if it's between -1 to 1, then it will be a compression. And then another important thing to note here is that if there's a negative in this value, so if this is a negative number, then the entire function is going to be flipped along the x-axis. So the x-axis, that's the one like this. So if the original function was like that, and there's a negative here, it'll now look like that. Right? Anyways, we'll look at more transitions on Desmos later. Okay, and then we have b right here. So b, it's similar to k, but it's not a vertical one, it's now a horizontal. And it's a little bit backwards. So let's say b equals 2. You might think, okay, that's a horizontal stretch by 2, or by a factor of 2. But it's actually the opposite. So the way I like to think of it is that it's 1 over b. So for example, 2 here be 1 over 2. So it's a horizontal stretch by 1 over 2, which isn't really a stretch anymore. Now it's a compression. So you would say, you don't want to say a fraction for the stretch or compression, or you don't want to say like a number less than 1. So instead of saying a compression by 2, or 1 over 2 I mean, or a stretch by 1 over 2, in this case you would say a compression by a factor of 2, right, in this case. So it's a little bit backwards because for k, if the value is 2, right, the value is 2, then it's a stretch by 2. But for b, if it's 2, then it's a compression by 2. So it's a little bit backwards. And then same goes for 1 over 2. It's like 1 over 1 over 2, which just equals to 2. So it's a vertical stretch by 2. It's a little bit confusing. And then if it's a negative number, so if this is a negative, then kind of like the negative here, except instead of the x-axis, it's the y-axis. So if it's a function that kind of looks like this, then this one's a little bit harder to draw. It would be more something like this. Okay, I think I got that right. That one's a little bit hard to draw, but it would be reflected along the y-axis there. Okay, and now it's the shifts. So we have a right here. Again, it's backwards, so anything that's like in this bracket here is kind of a bit backwards from what you'd think. So if a, because remember there's this negative sign here, so if a, let's say a equals negative 2. In your head you're probably thinking, okay, so it's 2 units to the left, right? Because it's negative, so it's to the left. But it's actually the opposite, because this negative will get multiplied by the negative there and it will become positive. So it's actually a, so a would actually be 2 to the right in this case. So always think opposite. So if it's negative, it becomes positive. If it's positive, it becomes negative. It's like if this number was positive 2, then it would actually be moved, it would be moved to the left instead, even though you'd think it would get moved to the right. And then finally there's D right here. D is probably the most straightforward one. It is the vertical. It's the vertical movement. So let's say you have a function like this, and then D is plus 3, for example. Then you just get moved 3 units up. So then it would look something like that. And then if D is like negative 3, for example, then it would just look something like this. So very straightforward. It's probably the most straightforward one. Let's look at Desmos to see how this works out. So I have a simple function here, x squared, simple parabola. Let's make it a little bit more complicated. So here, I'm going to add in all this stuff from before. I'm just going to replace everything with 1s right now so it doesn't have any effect. Okay, so let's look at the k value first. So this was vertical stretch. So if we make k, which is it's 1 right now, if we make it a number higher than 1, like a 5, see how it's now vertically stretched, right? It's going up quicker now. And then if we make it something like 0.5 or so, then it's so now it's more compressed. It looks like it was kind of squashed down. Okay, and that's what it looked like before. That's what it looks like now. So a little bit squished. And then again, if you put a negative 1 here, see how it's now reflected along the x-axis there. Okay, so that's what that one looks like. Let's look in here. So this one is B, which I said before as the horizontal stretch or compression. So again, I said it was backwards, right? So if I put in, say, a 3 from before, so remember, for k, if I put in a 3, it got stretched, right? If I put in a 3 for this one, now it looks like it got stretched, right? But remember, it's in the horizontal, right? So horizontal is like back and forth like this. So it actually got compressed horizontally. And then if I replace this with like 0.5, now it gets stretched horizontally, right? If we compare it to what it looked like before, that's what it looked like before. And then 0.5, it got stretched. This is probably the most confusing one here. So A, and again, remember it's backwards. So I set this as positive just so we could see the backwardness of it. Because if I set this to -2, So you would think that it would get moved to like this -2 one over here, right? But in fact, it got moved to +2, which makes sense because if we put in +2 for the number here, then the -2 cancels out with it, it just becomes 0, and then it's back at the origin, which makes sense, right? So it's backwards thinking, but it makes sense if you really think about it. And then again, same thing for +2, it goes to negative now, which is a bit backwards thinking, right? Okay. And then, actually, I guess we won't really talk about what happens if you do a like y-axis flip, because it won't change anything, right? If I put a negative there, it doesn't change anything because it just squared. So, and the function looks the exact same on both sides, so it wouldn't do anything. And then the vertical movement here, so again, if I do +3, it goes up by 3. -3, it goes down by 3. So that one's very easy to see. It makes sense, right? Pretty straightforward. All right. So that is everything for transformations. All right, so now we're learning about domain and range. So I have two functions here, and what we're going to do is state the domain and range for both of them. So this first one, f of x equals 4x squared minus 2x plus 1. So just to make it a little bit quicker here, I'm not gonna graph it myself. I'm just gonna use Desmos. On an actual exam, though, obviously you'd have to graph it yourself. We'll talk about that later in the course. But if you wanted to do it right now, you'd probably want to complete the square and then find the vertex that way. But for this case, we're not going to do it that way. Okay, so I can just do a quick little sketch of what this will look like. So remember, a parabola looks something like this. Yeah, so it's going to go positively up like that. I don't know what it's going to look like compared to the graph here. So yes, I don't know what it actually looks like. We'll take a look at Desmos for that, and you can solve it yourself like I already said before. But what we do know is that x can equal any real number. Okay, so basically what that means is that from here to there, x can be equal to anything. So there's no x value here that would make this equation like untrue or wrong or anything like that. So like all the way from like negative infinity all the way over here to positive infinity, x can be all that. So the way you're going to write that, so x can equal all real numbers. And then so that's all you're going to do for that. But then what about y? So for the range, basically wherever the vertex is, so wherever like this point, sure, I'll write that in a different color. So wherever this point right there is, it can't be anything below that, right? So anything over there will be false. So let's take a look at what Desmos says. So if we show this one right here, so so it starts up, and then let's see where the vertex is. So right at this point, so negative 0.25 and then 0.75. So we know that there can't be any y values that are under 0.75. So let's go back over here, and now for the range, so y has to be more or equal to 0.75. So we'll say 3/4. And then y can equal all real numbers. There we go. So y has to be over 3/4. Other than that, it can be anything else. So that's how we do that function. And then here's another one. So this one we can actually do without even looking at the Desmos here. So this is like a square root function, right? So what it will kind of look like is something like this, right? Now this one, let's see. So we have a vertical stretch by 2, so it's going a little bit more up, and then so x minus 3. So usually you'd think, okay, well that means we should go backwards 3, right? But remember, it's the opposite. So it's actually plus 3. So the very origin of this thing is going to start at x equals 3. So that is going to be 3 right there. And then it's also moved 8 up. So let's just draw what this will look like, a rough sketch. So something like this, right? So this is 3, 8. So now anything to the right of 3 should be valid, right? Because any x value that's above 3 should make this possible, right? Or even 3 itself should make it possible. So like even infinity, positive infinity should make this possible. But anything that makes this value right here negative is not possible. You can't have a negative square root. So basically what this is saying is that anything to the right of 3 or 3 itself is possible. So for the domain, we can say x has to be more or equal to 3. And then x can equal all real numbers. And then for y, so although it may not look like it, y actually also goes up to positive infinity, right? It doesn't really look like it because at the end when x increases in more and more and more, y only increases by a little bit, but it technically goes up to infinity. If we look over here at what this one will look like, so we can see it technically will go up to infinity even though it doesn't look like it. So, and then again, we can just look up here for proof. So yeah, it starts at 3, 8, and that's the farthest to the left and farthest down it will go. So if we go back over here, y cannot be anything under 8. So we're going to say for range y such that y has to be more or equal to 8. But it can equal all real numbers, or it equals all real numbers that are above 8. There we go. So that's just quick domain and range review. We'll talk about polynomial functions next. All right, let's look at polynomial functions. So first big question is, what is a polynomial function? So I have an example right here. This is an example of a polynomial function. And there's a few things that a polynomial function doesn't have. So the first thing it doesn't have is exponents that are non-integers. So for example, like 1/2 or 3/4, which you can see over here, these are non-integers. So it only has integer values as exponents. So like exponent of 2, exponent of 3, or in this case, there's an x right here, but there's an exponent of 0, right, which is also an integer. So exponents of whole numbers, basically. And then the next thing it does not have is it doesn't have exponents that are negatives. So like for example right here, -3 is not allowed. So there's no negatives, no negative exponents. And there's also variables. There can be more than one variable, so it could be like plus, like c over here as well. You could do that. There doesn't have to be just one type of variable. And then of course it obviously also has to be a function, so has to pass the vertical line test. Anyways, so that is what a polynomial function is. See, again, I already kind of answered this. What is not a polynomial function? So this one isn't a polynomial function because it is to the power of 1/2, and this one is the power of 3/4. So if there is like square roots at all, then it wouldn't be possible. And then this is to the power of -3, which again, it has to be over 0. So there's some important information when looking at a polynomial function. So for example, degrees, leading coefficient, and behavior, which will all link into sketching polynomial functions, which we'll talk about near the end. So there's three very important things. So first one is the degree. So degree is basically the highest exponent. So if there's exponent like 4, 3, 2, or 1, the highest one would be 4. So the polynomial function would have a degree of 4. So in this case, the polynomial function has a degree of 3, right? But if this, let's say this 2 was replaced by like a 5, for example, then it would be a 5, or it would be degree 5. Yeah, and each one of these powers here has a different name for it. So if it's, say, power to 1, so if it was like x, or like, here I'll do f of x, I'll fix this. So f of x equals 2x, then that would be a linear function because it's to the power of 1, right? But if this was a 2, then it would be a quadratic. If it was a 3, then it would be cubic. 4, it would be a quartic, and then 5 would be quintic. You might need to know those for your exams, so I would make sure you remember those. So the degree has a couple important components to it. So it says the overall shape of what it will look like. So for example, if it is a odd number, so like 1, 3, or 5, etc., then the start and end will be at different ends. So for example, if we just do a single straight line, it'll look something like that, while 3 on the other hand will look something like this, right? And then 5 will look something more like this. So it starts and ends in either the starts in negative and then ends in positive, starts negative, ends positive, and these two are opposite. So it could be the other way as well, right? It could be, for example, it could start like up here and then come down, but it's going to start either positive or negative and then end in the opposite. So in this case, it starts positive and ends negative. And then no matter what, it could also have a different shape to it. For example, if it's something, it could have a shape of like this, for example, but you can tell automatically that this has to be an odd numbered, or the degree has to be odd, because they start and end at different spots, right? This one starts negative, this one starts positive. So if it starts and ends in either negative or positive, different sides, then that means it's odd. Well, even on the other hand, so that would be like 2, 4, 6, 2, 4, and 6. Then it's going to look something like this. It's going to look like a quadratic, like that, right? So, and they're going to start and end in the same area. So positive, positive, or negative, negative. They're going to start and end in the same spot. So let's say I have a function that looks something like this. Would this be positive? Or sorry, would this be odd or even? The degree be odd or even? So it would be odd, right? Because they both end in different spots. So this one's negative, that one's positive. So another thing the degree talks about is that it explains how many turning points a function could have, or the max number of turning points, sorry. So, for example, if we have a function that looks like this, up, down like this, so we can see there's about 1 and 2 turning points, right? So by looking at this function here, we can tell that it has to be at least power of 3, right? Because if it was power of 2, then it would start and end like this. It would only have 1 turning point. If it was power 1, then it would just go right through. So it has to be at least a power of 3. It could be more than that, though. It's hard to tell just by looking at it. We'll talk about more about like orders later on, about what that means later on in the video. and how to actually draw a function properly, but for now it's a little bit hard to tell. So let's write in a formula here. So number of turning points, I'm just going to say number of TP plus 1 equals minimum degree number. And that makes sense because if you have like a quadratic, for example, there's only one turning point, which means if you add 1 to that, it's a degree 2, right? So that makes sense. And then another thing the degree tells you is the maximum number of x-intercepts. So number of x-intercepts minimum number of minimum degree. So again, it could be like power 8, but if it's just like x to the power of 8 plus like 2, for example, then it's going to look something like this. Or sorry, it'll be more steep. It'll look like this, and there won't be any x-intercepts. So just because there's no x-intercepts doesn't mean that there is like no degree to it. So it's minimum number, it's minimum degree, right? So if there's 3 x-intercepts, it doesn't mean that there can't be a higher degree than 3, or if there's 0 x-intercepts, it doesn't mean it has a degree of 0. But if it has a degree of 5, then it can only have 5 x-intercepts, so it can't have any more than that. Okay, so the next thing we're going to talk about is the leading coefficient. So for example, let me just state what that is. So leading coefficient for the highest power is what we're talking about here. So if you have, let's say, x to the power 4 minus x to the power 3, and then let's say plus 100 x, you're only talking about what's in front of the highest degree. So this number right here, which in this case would be 1 right now. So actually I'll change it so it's something a bit different. Let's do 3. Okay. And whether this number is positive or negative is going to basically point the direction of the final direction of the function. So if it's positive, and we already talked about this before, so like an odd function, for example, looks something like this, right? So it starts and ends in opposite, neither negative or positive, while an even kind of goes like this, right? So it starts and ends in the same one. So whether this is positive or negative is going to affect whether it's going like this or whether it's going like that. Okay, so if this number is positive, then it's going to look like this. So it's going to end positive, it's going to start negative. And same thing for even here, it's going to start positive, it's going to end positive. If this thing is negative though, so let's say it's negative 3, then this is going to end negative and it's going to start positive. And same with this. They're both going to end negative. And it doesn't matter what any of this other stuff is. Okay, this could be like, you could have as many zeros as you wanted on this number here. It wouldn't affect it. At the start, it may be in or near close to 0. It may look like this one has like the most like power, I'll say. But x to the power of 4, if you put like x equals infinity, then this number is going to equal, then like this number right here is going to be the primary number in deciding direction. So again, if it's negative, then for an odd function, it's going to start positive and negative. If it's positive, then it will start negative and positive. And then for even, if it's positive, it'll start up here, end up here, so positive, positive. Oh, if it's negative, then it will go negative, negative. So this all ties into end behavior, which I kind of already talked about with this leading coefficient thing. But I'll just go over it again, and there's also like a bit of form needed for this. So the way you're going to write end behavior, so it's x, when x approaches this positive infinity, and then you're going to say y approaches, and then whatever it approaches. So I'll leave that blank for now. And as x approaches negative infinity, y approaches, I'll just leave it blank. So yeah, I'll leave it blank for now. So this is going to depend on whether the function is even or odd, as in if the degree is even or odd, and what the leading coefficient is. So we've kind of already talked about this, but we'll do some examples. So let's say 3x cubed minus 2x. What would be the end behavior of this one? So let's just do a quick sketch of what an odd function is, because remember there's 3 there. So an odd function is either going to look like this, or it's going to look like this, right? So it depends on what the leading coefficient is. So in this case it's positive, which means it starts negative, ends positive. So in this case we can look at this and say, well, when x is approaching positive infinity, which is in this area over here, then y is going to be approaching positive infinity. Okay, and then so let's look at this one right over here. So when x approaches negative infinity, so that's in this area, we can see that y is approaching negative infinity, right? Like negative infinity is down there, which is where it's pointed. So let's look at a different one. So let's say it's negative x to the power of 4 plus, I'm going to say, a very, very, very large number here, x squared. So it doesn't matter what this final number is. It doesn't, you can just like erase it. It does not matter. You can just completely ignore it, because remember, it's only the one with the highest exponent. So in this case it's even, right? So let's just draw what an even one looks like. So it either is going to look like this, or it's going to look like this. And then I'll look at that, it's negative, so it's going to be this one, right? So we can say, well, in this case, that when y approaches negative infinity, or sorry, when x approaches positive infinity, this is going to approach negative infinity, and then this is going to also approach negative infinity. All right, very straightforward. So just to do a quick little review here. So if it is odd, then it's going to be opposite, right? So odd, I'll say opposite, opposite end behavior, and then even is the same. So just remember that. Odd is opposite, even is the same. Let's learn about x and y intercepts. So I have 2 polynomial functions here, and now we're going to try to find the x and the y intercepts. So the x-intercept, we'll do that first for this function. So remember what x-intercept means. That means whenever it hits the x-axis, which is this one right here. So whenever f of x equals 0, so whenever 0 equals all this, that is an x-intercept. So what values for x will make this equal to 0? Well, anytime one of these terms here, so for example x right here, or x minus 2, it's cubed also, so x minus 2 cubed, or x plus 1 equals 0, this whole thing is going to equal 0, because Like let's say in this case x equals 0. So if I set x equal to 0 here, this entire thing will become equal to 0. So it'll be an x-intercept. Because 0 times all this, no matter what this value is here, even if it's like a billion times 0 is still 0. So anyways, so the x-intercepts for this case, so well, we can look right off the bat when x equals 0. So boom, we got 0 as one of the x-intercepts. And now let's do this one. So x minus 2, and then it's cubed when this equals 0. So the cubed in this case, it doesn't matter. You're going to cube root both sides. So you're going to take the cube root of 0, which is just equal to 0. So this would just equal 0 here. And then you get x negative 2. And then you just move the 2 to the other side, and then you get x equals 2. So there's another x-intercept. And then finally x plus 1. So x plus 1 equals 0. And then x equals negative 1. There we go. Pretty straightforward. So all the x-intercepts would be 0, 2, and then negative 1. And then y-intercept. So y-intercept is when it is along the y-axis. So when x equals 0. So in this case, you just fill in x. So it'd be like f of 0. F of, oh crap. F is 0. There we go. And then this x in front here would just be turned to 0. So it'd be like multiplying 0 times 0 minus 2, which is cubed, and then 0 plus 1. And then this 0 just gets multiplied in here. So it just results as 0. So that would be, so y-intercept is equal to 0, 0. So an x-intercept and y-intercept, they can be the same thing. Actually, here I'll write y-intercept. There we go. All right, let's look at this one. So let's solve for the x-intercepts first. So 0 equals x minus 3, and then it's cubed, or sorry, squared. So you're going to do square root of both sides. Square root of 0 is equal to 0. So 0 equals x minus 3, x equals 3. And then this one right here, we can just look at it really easy. If x equals negative 4, then this whole term would equal 0. So without doing the math there, I'll just write negative 4. And then this one's a little bit trickier. So 3x minus 2 equals 0. And then just move the 2 to the other side, and you get x equals 2 divided by 3. X equals 2 over 3. So those are the 3 x-intercepts, and then let's do y-intercept. So g of 0 equals 0 minus 3 squared, and then 0 plus 4 0 times 3 minus 2. So this would be negative 3 squared, which is just equal to 9. This would just be 4. This would be 0 times 3, which is 0 minus 2, so negative 2. And then this should all equal negative 72. There we go. So let's learn about order. So the order is basically the exponent on a root. So let's look at this x. So let's look at the top one here. So x minus 2, and then it's cubed. So this would be order 3. Okay? Well, if it was like x minus 2, and then it was like squared, for example, then it would be order 2. So this is order 3, order 2, x minus 1, sorry, x minus 2 to the power 1 would be order 1. So anyways, you get the idea. So whatever exponent is on that value, that's the order. And now these orders mean different things. So for example, when you're sketching your graph here, let's say we have x minus 2, so again, where would that be? So that would be when x is positive 2, right? So when x is positive 2, which is about right there, so that's the x-intercept. So for a number like 1 here, that would mean that the line coming through here, when you draw your sketch, is going to go right through. So like this. That would be order 1. So here, I'll write that in. Order 1. While order 2, you can think of like a parabola, for example. It's going to bounce right off. So it's going to come in like this, and then it's going to just touch that point, and then it's going to come right back out. So it's going to look something like this. So that is order 2. While order 3 would be kind of like 1, but it's a little bit different. So it's described as like a squiggle kind of. So if I do like an x to the power 3, you can kind of see the squiggle there. And then it would be the same sort of thing like this, for example. See how it makes that squiggle? Oh. So it's a little bit hard to see. Oh. So here, I'll zoom out. But you can see it kind of comes up, and then it comes close, and then it shoots back up again. So you can kind of see it there. It looks different from like 1, for example, though, right? So that is order 3. Order 3. There we go. And this all has to do with when you're drawing your functions. So let's do some sketching stuff now. So we're going to take everything we just learned, and we're going to apply it all together now. So let's do this first one first. This one right over here. We kind of already looked at it. We already have all the x-intercepts, y-intercepts, so it should be pretty straightforward. So first off, I'm just going to draw this. And then first thing I like to do is I like to just put in all the x-intercepts. So we have 0 as 1. Here, I'll draw this in a different color. There's 0, 0. Oh. And then let me make this a bit bigger. There we go. And then also x equals 2. So we'll set that to like over here. And then x equals -1. So that's like right there. And then of course y-intercept is also the same thing as this x-intercept here, so that's also right there. And then I'll just label the points. So actually no, sorry, before I do that, so let's take a look. What is the degree of this? Remember we just talked about degrees a bit earlier, so it may look like this is a degree 3 because there's like the 3 power 3 right here, and there's also 3 x's. But this is actually a degree 5. So the reason why you can tell that is you're basically going to take the power of all these numbers here, and you're just going to combine them together. So like 1 plus 3 plus 1 is equal to 5. So it would be degree 5. And this one over here, so you got 2, there's imaginary 1 there, imaginary 1, you add them together, this would be degree 4. So if you basically expanded out the entire, all these different like polynomials here, then that's what you'd get. Okay. So if we know that it's degree 5, we know that it is it's an odd one, right? So if remember before, that means it starts and ends in different spots. So it's going to start up there, end up there. And then let's look at the number in front. So We have a positive in front there, which means that it's going to look like this. So it's going to end up here, finish down there somewhere. It doesn't matter exactly. It doesn't have to be perfectly to scale. This is just a sketch for now. So this is what it will kind of look like. And now let's look at our orders. So x, so this x one right there, it's going to be straight through. Actually, let's start from the left. So x plus 1. If we look at this, oh crap. If we look at that, it's going to be straight through. So it's going to look something like this. And then it has to eventually get to this point right here. So it's going to turn around somewhere up here, and it's going to come down here. Now x, let's see, it's power or to order 1, so it's going to come right through, and then it's going to come back, wrap around here, and then remember it's going to be a squiggle, right? Because it's power of or order 3, so it's going to look something like this. Let me do that again. So up here, to come in, there we go, something like that. So let's look at Desmos to see if we got that right. Is it x plus 1, then x. Okay, so pretty similar to the one that I drew here. Again, the scale is a little bit off, but looks very similar. So I'd say that's pretty accurate. Let's do a different one. So I'm going to make up one for this. So I'm going to say f of x equals -2 x minus 4 do power 2, and then x plus 5 and then 3 minus x. Okay, so one thing I drew in here, or I put in here, that you have to watch out for is negatives in front of the x. So this is going to throw off the whole thing, because it looks like, so it looks like this one's negative, and you can tell that if you add 2 plus 1 plus 1 you get 4, so it looks like it's an even one. That's going to start and end down like this. But if I were to put this in Desmos, it actually won't end like that. And the reason why that is because of this negative right here in front. This negative is going to throw off the entire thing. So we have to take out that negative. And the way you're going to do that is you're just going to factor out a negative over here. So you're basically going to multiply out a negative in this term. It's going to become like negative bracket, it's become -3 plus x. So that's what this thing's going to become. So here, let me fix this. So negative, and then this is going to become -3 plus x. And now this negative is going to get moved all the way to the front here, and it's going to multiply with that negative, and they're going to cancel out. So I'll show how this kind of works on Desmos. So what was it? -2x, then x minus 4 squared plus, not plus, x plus 5. Okay, so look at this, right? It's going upwards, even though you can see the negative there. It shouldn't, you think it shouldn't do that, right? Because it has a negative in front. And then, so after fixing it there, here, I'll just copy and paste it. So after you fix the negatives this becomes positive, this becomes negative, and you can see they're equal to each other. Right, so like these two functions are equal to each other. Right, so anyways, so that's just an important thing to watch out for. And then this number in front here is going to decide what direction it points in. So we already decided, well, it's order 4. Oops, sorry. It's order 4 and, or sorry, not order 4, it's degree 4, and then it also is positive. So we decided it's going to end positive, or sorry, start positive, end positive. So it's going to end like this, right? Actually, let's do the end behavior then. So as x approaches negative infinity, y is going to approach positive infinity. And as x approaches positive infinity, y is going to approach negative infinity. There we go. And now let's draw this. So it's going to end something like this. There are a few more things we have to do though. So we have to find the x-intercepts first. Let's go back here. So we'll do x minus 4 squared equals 0. So again, you can just take away the squared, square root both sides, and then you get x equals 4. So there's one of the roots. And then this one we can just tell is negative 5. And then this one we can tell is positive 3. So plus 3. So let's write that in order. So negative 5, 3, and then 4. And then 4 is, I'm going to say O2. So order 2. So we'll start with the negative 5. So I will draw this in a different color again. Negative 5 is about right there, and then we have 3, and then we have 4. Nice. So negative 5 is straight through. So this one's going to come up. Let's go right through like this. Actually, let's do the y-intercept as well. So for that one, remember, you just set x equal to 0. So f of 0 There we go. And then just solve. So like this will be 2 times 16 times 5 times negative 3. Put into your calculator. I got negative 480, so I'm just going to check back on Desmos to make sure this is all good. Oh, missed it. Where is it? Right here. Okay, good. So that one's right. So again, this isn't to scale. We'll say like right over down here, and then you're going to want to make sure that you're saying what this is. Actually, sorry. This is 0, comma, negative 480. And it's going to come up towards this one. Let's see. So 3, we said it goes right through because it's order 1, so it's going to go right through, and then it's going to turn around. And then for this one, remember, it's going to bounce off. And it also makes sense too. Actually, this looks like a bit like a V. Let me fix that. So up, around, and then it's going to look like a parabola. So something like that. There we go. And that's how you sketch this one. And then, of course, also label these points as well. So you just want to point out that that's like 4, that's 3, that's -5, so just make sure you're doing that so your teacher knows. Okay, so that's sketching polynomials. I have one more thing, which I'll skip right ahead to. Alright, so the final thing we're going to do, which is just a small little thing, is called the nth difference. So there's like first difference, second difference, third difference. So nth difference just means like any variable difference. So it'll make more sense once I get started. It's kind of hard to explain, but for this function right here, I have a kind of like a table of values right here. It's not really a table, but so I have like -3 all the way up to 3, and then what the y value would equal for all those numbers. So if you remember from before, when you do first difference, that is like finding the difference between all the numbers at the start, okay? While second difference is then finding the differences of all those numbers and then finding the difference between all those new numbers you just found. And then third difference would be, anyways, it goes on and on and on. So there's actually a pattern for this. So the degree of the polynomial, so in this case, the degree 3 is basically the n value. So for this function right here, it would be the third difference. And the third difference for this function would have the same number for every single one. Okay, so anyways, we'll find out what that is, and I'll show you a pattern on how you can find it very quickly. There is like a pattern to it, but it's basically what the function will eventually be continuously as. So it'll have a continuous number that it is for every single one. In this case, for the third difference. If it was, let's say, like a 5, if this was like a 5 instead, then it would be fifth difference would be a certain number. Anyways, it'll make more sense once I get started. So let's do the first difference first. So this is first. So we're going to find the difference between these two numbers. So what do you have to do to -116 to get -30? Well, you're going to add 86 to it. And this is very continuous, so I'll kind of skip ahead a little bit. Okay, so I got the first difference. Again, all these numbers aren't the same, so let's go again. We're going to do second difference now. So we're going to do the same thing again, but now with the new numbers here. Okay, so there's second difference. And finally, third difference. So this is the one that should all have the same value. And then, so it does. So these are all equal to +24. So for your test, you don't have to know why these all equal the same number. You'll learn more about that when you do calculus. But you do have to know that they all equal the same number. So if you're given a table of values without the original function, so without this thing right here, I just kind of did it so I can show a pattern. Then you can use this table of values here to find basically the degree of the function. And you can actually find the coefficient as well that's in the front. So the cool thing about this number right here, so the cool thing about this number right here is that that number is actually equal to, delta n is the number, I'm going to call it the nth difference, is equal to the factorial of the degree, so in this case 3. Basically the factorial, that just means, let's say for 3, it's all the numbers that come before 3, so times 2 times 1. So the factorial of 3 is just equal to 6. Right, so the factorial of, I'll call it n, and then that is all multiplied by the coefficient in the front here. So I'll just call that k. There we go. I don't know if this explanation point is supposed to be in the front or the back. I forget, but basically factorial of this multiplied by k. So in this case, it's 3 factorial, so 3 factorial, and then multiplied by 4. Yeah, so this is equal to 6 times 4, which is, equal to 24. So we got the right answer. And you'll learn more about like why this is in calculus when you eventually take it. But that is how that works. So that is nth difference. So if I were to say something like negative 5 x to the power of 5, the nth difference in this case would be factorial of 5 all multiplied by negative 5, which would be, what would that be? That would be negative 160. So the nth difference, or the fifth difference for this function would be negative 600. Okay. And that's all for this video. So I'm going to there'll be another part 2 of polynomials in the next one, and then maybe also rational functions. I haven't decided yet. Alright, so that's all for this one.